Okay, so we are going to calculate electron heat capacity of electron gas. Okay, we have seen earlier the classically the per particle electron specific heat is 3/2 kb. Okay, and if the n particle, the total specific heat of electron gas, okay, with of n particle is 3/2 nkb. Okay, now we are going to use Sommerfeld theory. Okay, so as last time I told you that if we apply Pauli exclusive principle and Fermi drag distribution function, so that this discrepancy, okay, that in specific heat value can be removed. So I'm not going to use a lengthy derivation. Okay, I will use some trick. Okay, a small trick to make it simple. Okay, because we need only that expression for specific heat, not derivation is not that much important. Okay, so we know that classically, okay, or classical statical mechanics okay, predicts that electron is specific heat, okay, electron specific heat is 3/2 kb, okay, for electron gas of n particle. We can write 3/2 nkb. Okay, and I told you that this specific heat is quite high what we measure experimentally. Okay, compared to experimentally observed value, this value is quite high. And last time also when we were discussing this one, I told you this problems arises mainly because we are counting all the n particles. Okay, but actual case all the n particles are not contributing to specific heat. Only electrons which are near to Fermi level, okay, that's a fraction of those electrons only contributing to specific heat. Okay, so observed discrepancy, okay, observed discrepancy, okay, is removed, okay, if we use assume electrons are fermions, we use Fermi drag statistics, okay, and along with we apply Pauli exclusion principle. Okay, so of course when we are using density of state, okay, we are assuming that each state is a two particles, so we are using Pauli exclusive principle also. Okay, as well as we are using Fermi drag statistics also. Okay, now let me calculate the specific heat using the concept of density of states. So density of state and using the Fermi drag statistics. Okay, so we know that energy can be written as, how can we write energy? We know the total energy. Okay, total energy can be written as 0 to infinite limit e power. Okay, and if I write density of state by dE or Ge, whatever you want to write, dE. Okay, and we need to multiply this by Fermi drag function. Okay, which is a function of temperature. Okay, and this time I'm not taking this time I'm not taking this T. Okay, 0, and then we have D. Okay, so this is my expression for total energy, isn't it? Now I need to calculate the specific heat. So in order to calculate specific heat, I need to, okay, differentiate this equation, okay, del U upon with respect to temperature, okay. So if I differentiate, okay, this will become d by dt 0 to infinite E d, okay, omega function as a temperature function of temperature, okay. Now I can these two operators are always interchangeable, okay. I can bring this differential inside, so E d, okay, and I can put here this d by dt, this dt is a temperature, okay, f e t t, okay. Now let me use some integration, okay. Here to simplify this integration, I'm using one integration whose value is 0. So I'm taking now e of ef d by dt, okay, integration 0 to infinite, okay. If I take g de fe de, okay, I'm taking this integration, okay. And all of you know what is the meaning of this integration. This is what, this is my number, total number of particle. So if I use this one, this will give me ef, and this give me dn by dt, okay. And the variation of particle with temperature is 0, okay. Particles of particle number do not change very, okay, only the side, okay, a little bit, but almost this we can, this derivative we can take as 0, okay. So that means I can take this integration I, so the value of this integration I is equals to ef, okay, 0 to infinite, okay, d d, and if, and you can also take out de also, because now I will use state that only at Fermi levels, okay. So let us now d fe upon dt, okay, and d, and this is a constant, so if you want you can bring here also inside also, okay, ef, and this value is 0. Now what I'm doing, since this integration is 0, okay, okay, this value is 0, so value, this value can be added anywhere, okay. I can add this integration here or subtract this integration here, okay, because this is 0, so this my expression will not change, okay. So now what I'm doing, I am writing again this value c, I'm writing this specific heat value, okay. And what I'm doing, I am subtracting this integration from here, 0 to add ef d df upon dt, okay, d, because this is 0, so if I add here nothing will change, okay. Now let me simplify this cv, okay. Now I can bring this, because minus I can bring here, because these two things are common here, so I can write this as a 0 e minus ef, okay, d, okay, d by dt f et d, okay. This is my expression for specific heat, okay. Now what I can do, okay, so once I have the specific heat, let us simplify it further, okay. Now we want the differentiation of Fermi Dirac distribution function here, okay. So I need to differentiate this one, okay. Please you also do it yourself, okay, so that there should not be a mistake. So now I have this Fermi Dirac distribution function, okay. So this I can write as 1 plus exponential, okay, E minus EF by KT, KBT or KT, okay. Now just differentiate, this is a function of temperature. So differentiate dFE upon dt, okay. This will give me what? This will give me what? 1 plus exponential E minus EF by KBT, okay, square. And again, if we differentiate this one, okay, 1 plus this one. So again I get exponential E minus EF upon KBT, okay. And if I differentiate this thing, so I have E minus EF, KB is there, okay. And if I differentiate, so this is already minus there, okay, if I 1 plus x, okay. And if I do 1 by t, this minus will come and this will come 1 by t square, okay. So this is the differentiation, okay. Now let me plug this value in the integration. So I have integration CV, okay, 0 to infinite, okay. I have E minus EF, so is become square. E minus EF will become square, okay. I have KB T square. Then I have a DE, okay. DE, E also, no? E minus EF square DE, okay. And what is there? Nothing. D, okay. And this expression, sorry, this full expression I have to write, okay. So this full expression if I write, so this KBT square is there, okay. And this here, this we have, okay, 1 upon 1 plus exponential E minus EF upon KBT square, okay. D and density state function D, okay. Now I can bring this density state function outward because I'm using only states near to Fermi level, okay. And so you can write this one, okay. You can bring okay, and I'm multiplying here by KB, so 1 KB will come out, okay. And I'm putting this value as a x. So put the value, just solve this, simplify this integration by substitution. So I'm putting E minus EF, okay, KBT as x, okay. So if I put x, okay, so at when E is 0, okay, when E is 0, my x become tends to minus EF by KBT, okay. And when E tends to infinite, okay, x also tends to infinite. And if I differentiate this one, so if I differentiate, I get E minus dx value, no? I want dx. So if I differentiate with respect to dE, okay, so this become 1 by KBT, okay, dE by dx, okay. So we can substitute this value. So I want dE, so dE will be what? dE will be KBT dx, okay. So now let me put these values and simplify. Okay, so if I put these values, I have this KB outside, this become x square, limit become minus EF upon KBT, okay, and they are infinite. And then I have a x square, okay, x square upon 1 plus x, 1 plus x square, Okay. 1 plus x square, no? Ex plus 1 square, sorry, ex plus 1 ex.
इंटीग्रेशन के
Okay, so x square 1 plus ex square x square and kbt square. Okay, so is it correct?
सर एक्सपोनेंशियल के अंदर एक और इंटीग्रेशन के अंदर एक और एक्सपोनेंशियल टर्म आना चाहिए।
क्यों?
डिफरेंशिएट करेंगे तो एक्सपोनेंशियल पावर e माइनस ई एफ बाई के टी भी तो आ रहा है उसके
हाँ, तो ex आएगा ऊपर ना। अच्छा, करेक्ट, ex आएगा इधर। ओके, यहाँ पे हाँ, ये 1 टर्म वाज मोर। ओके, एक्सपोनेंशियल e माइनस ई एफ बाई के बी टी। Okay, this term was there, and this become x square and this power e power x 1 plus ex by square। और क्या आएगा? dx करने से d करने से kbt। ओके, सो kbt कहाँ आएगा? नीचे
सर
आएगा
वो
ऊपर?
बट ई माइनस ई एफ ऊपर वाले में ई माइनस ई एफ का होल स्क्वायर आपने लिखा हुआ है अपॉन के इसी में लास्ट इक्वेशन से पहले वाली इक्वेशन सेकंड लास्ट।
इसमें ना?
हाँ 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 हाँ।
ये तो कर दिया ना मैंने, ये तो कर
और
दिया।
इसमें नीचे ये के बी स्क्वायर है कि के बी है?
ये वाला, ये kb है,
नीचे
kb है, kb है, तो मैंने kb स्क्वायर कर दिया और kb क्या कर दिया था ना, ताकि मैं इसको x, ताकि मैं इसको x बना सकूं। ओके
ओके सर।
okay, now what you can solve, tell me what is the coming if you solve this one। okay, and और क्या आएगा? it will should come this much। okay, if I done mistake please correct। okay, this much should come। और क्या आना चाहिए? t आना चाहिए क्या? टेम्परेचर kbt, हाँ, यहाँ से kbt आएगा तो kb स्क्वायर t, it should come। okay, and then if I solve it further, बस एक स्टेप में हो जाएगा। and now we have this now generally our kbt is less than ef। okay, if I take temperature corresponding to Fermi energy, the temperature Fermi energy is 4 to 5 electron volt for metals। okay, so this will give you around 3000 Kelvin, and the room temperature be at 300। okay, 300 400, that is compared to this one, this energy is very low, so I can make this limit also infinite। so this will give me cb def, okay, kb square t, okay, and this will give me minus infinite to infinite x square ex 1 plus ex square dx। okay, just check it, I'm doing wrong, right or wrong। okay, so now this is standard integration। okay, this integration value is pi square by 3। okay, so I get kb square t def। okay, and this integration is pi square by 3। okay, now still I can solve this one। okay, so yesterday we have seen I have written def। okay, I have written de in terms of particles, so this was 3 by 2 n by e। yesterday I have written the density state in terms of energy। okay, in terms of energy, and here is the Fermi energy, so you can put f here, you can put f here। okay, so if you plug here, I can write, okay, the specific heat as pi square by 3 kb square t, and this is particle 3 by 2 n ef। and if you cancel 3 cancel, okay, so I have c is equal to pi square by 2। okay, I have kb square t, I have n also। okay, and ef I can write in terms of temperature, Fermi temperature। okay, so 1 power removed। so this is the final expression। okay, cv, okay, I have pi square by 2 n kb T upon TF. Okay, so this is the calculation when we do by Sommerfeld theory. Okay, so my CV electronic space heat is proportional to, or I can write as a gamma T. Okay, proportional to temperature. Okay, and this can be written as a CV equals to gamma T electronic. Okay, CV electronic. Yes. Okay. Now we know the total specific heat. Total specific heat has a phonon contribution also. Okay. So if I want to write the specific heat for metal, okay. So this is, I know this is AT cube. Okay, plus gamma or B, whatever you want to write, gamma T. Okay, so this is the specific heat of metals, okay, or solids. Especially metal has a contribution here and low temperature. Metal has a lot of electrons, so this term will come. Solid, if you take insulator, you don't have electrons, so this term is not important. Only specific heat is governed by your phonons. Okay, phonon vibration. So this will be specific heat of metal. Okay. Now, if I compare this specific heat with classical value, okay. So classical value is very high. So if I calculate the CV electronics, okay, which we call calculated with CV electronic classical, okay. So this will come out as pi square by 2 n kb T upon TF, and that is 3 by 2 n kb. Okay, that is the specific classically what we have seen earlier. Now, if I solve this one, okay, so this gave me, this will cancel out. Okay, so the ratio will be pi square. This ratio sometimes they ask kb pi square by 3 T by TF. Okay, this is the ratio. Okay, and as I told you earlier, this is if you take this ratio, okay, say this is 300, suppose this is 300 room temperature and this is 3000, so this ratio is itself 1 by 10. Okay, not 1 by 10, 1 by 100. Okay, 1 by 100, and then this ratio, so this ratio almost comes out as 1 by 40. Okay, so we exactly do that is, okay, 1 by 40 of class this classically calculated values. Okay, now this derivation can be done, okay, in very simple manner also, and that expression we sometime we may require. Okay, so just please note down these things. So can I remove erase this one? Okay, so I'm erasing this one. Well, please remember this expression. Okay, and tell me when I ask later. Okay, why don't I have very low memory? I cannot remember things. Okay, so now generally we write Fermi energy. Okay, so Fermi energy is generally we write, earlier we were writing at T is equal to 0. Okay, so T is equal to Fermi energy is nothing, it's a chemical potential, isn't it? So chemical potential. So but in general, if you write potential Fermi energy, it is a weak function of temperature. Okay, if I write temperature dependence of this Fermi level, okay, so the exact expression, we are not deriving this expression. Okay, this expression is kBT upon E F naught, okay, square. Okay, this is the temperature dependence of Fermi level, but this dependence is very small. Okay, so this term is kB by T very small, very negligible compared to kBT. I told you the EF is very less. Okay, so the dependence on temperature of Fermi level is very weak, and We expect this also, na? Because Fermi energy generally depends on what? Density. If I take solid, okay, with temperature, my density do not vary, na? My volume volume does not change when I'm heating sample, unless I am doing temperature close to this Fermi energy, nothing happening to sample. Okay, so the dependencies should be very weak. Okay, and that's we can see here the Fermi energy is a weak function of temperature. Okay, similarly, yesterday we have seen the particle, okay, average energy particle. Okay, that also we have calculated on t is equal to 0, and this is also function of temperature, and it is given by pi square 12, okay, kbt pf naught square. Okay, this is the energy. Okay, now if I want that specific heat, I can simply differentiate this equation d by dt. Okay, so if I differentiate this one, okay, what will get? E naught. Okay, and if I solve this one, this comes 5 by 6 pi square kb square ef naught square and t. Okay, and the value of this per particle I'm calculating. Okay, per average energy, you have to multiply by n also, and I know the average energy per particle is 3 by 5 ef naught. Okay, so if I put this value here, so I get 3 by 5 ef naught. Okay, 5 by 6 pi square. Okay, kb square ef naught t. Okay, so square cancel. Okay, 5 cancel, this is 1 by 2. Okay, so I will be having cv, this is cv per particle, cv electronic particle, this is a particle, one particle. Okay, and if I solve this one, this will give me cv electronic. Okay, pi square by 2. Okay, again same expression coming, kb square.
Sir,
1 minute. And if I put ef is equal to kbt, kbtf. Okay, and this is a t, so kb cancel, so I get pi square by 2. Okay, kb. Yes, tell me.
here why we read 3 by 5 EF naught, sir?
This is the average energy yesterday we calculated, na? 3 dimension average energy per particle.
Yes, it is 3 dimension.
Yeah, 3 by 5. Okay, and this is for, and if I want a solid, if I have n particle, okay, so cv of solid metal, okay, I get to write multiply by n kb, so I'm getting exactly same expression, n kb t by tf. Okay, so this way you should also remember, because they can form question on here also. Okay, they can do some here value change, some dimension value, some they can ask you this type of things also. Okay, so this is your specific heat. Okay, we have accurately calculated specific heat. Okay, now let me discuss the electrical conductivity. Okay, now second half of the class, you have a class test, okay, of superconductivity. Just a small 10 question, it will not take more than 10 to 15 minutes. This is some concept and memory based question. So I will share the link after this class. Please see this and solve them. Okay, Now
electron theory, this is how many topics are left?
in this only band theory is left. Okay, band theory is left, and we'll do for preparation for gate. Okay, that time in January, February. Then I may include one or two topic more here. Okay, so after this, just band theory is left, and for some student, they did not learn this crystal structure. For them, okay, we will arrange the classes for crystal structure, and if you chapters are more, that will see. Okay, first that important topic for exam, marks wise important topic is electronics. Okay, na? Because weightage is more. Okay, weightage every paper is the same weightage, but generally if you see last so many years paper, okay, the marks weightage is more for electronics. Okay, so I want to put more classes on electronics. Okay, that will take a lot of classes. Okay? Because we have analog and digital both, so that will itself will take at least 60 to 70 hours class. Okay,
So in this subject, weightage is of how many marks?
but that is not fixed. No, that depend, that variation is there, but generally the variation is not as like variation. Okay, if you can see the last year's statics. Okay, so you see sometimes they ask 3-4 questions, sometimes ask they 1-2 questions. Gate generally they ask for solid. Okay, the almost uniform weightage is there, but in net the dependence depends. Okay, sometimes they give solid state more, sometimes they give less. So whatever we are doing, okay, that is enough. Okay, you will able to do solve the problems. Okay.
Sir,
Hmm.
and the most important topics in solid are like crystal structures and lattice vibration, and or this topic is also very important.
जो मैं करा रहा हूँ, whatever we are doing, that's important. Okay, and you can see there is nothing much difficulty. All are similar type of concepts. Okay, the most important thing is density of states. Okay, once you know the density of states, you understand the dispersion relations. Okay, and then they're asking the same things again and again. If you see last 10-15 years papers, same questions they're asking, mainly based on concept of density of states. Okay, so whatever we are doing, that is enough. Okay, you can easily attempt the questions, and still we have time. The exam is gate exam is in February, and we also don't know when is the your CSIR net exam. Okay, so if the exams goes get delay, okay, we are first expecting in December. Actually it will not be happen in December, but we are preparing for in December. If it is in December, so we will complete most of the syllabus, and if we get delay, then we will do the remaining topic which are not much significant or have less contribution to papers if we analyze the last year papers. Okay, so that we will do later. Okay.
Okay, sir.
Okay.
Thank you.
So now I'm not deriving the formula for electric conductivity because that's need Sommerfeld Boltzmann equations. Okay, the unnecessary waste of time, because we are not going to get any new information by solving this derivation, and the conductivity expression is not different what we got from classical theory. Okay, so the main concept, okay, of conductivity that were included in the Dode theory itself. Okay, so Dode told that the electric conductivity is given by Ne square tau upon m. Okay, you assume N square tau upon f. Okay, and when you use this is for Dode theory. Okay, Dode's theory. Sommerfeld, using Sommerfeld theory or quantum theory. Okay, so the difference is not much. Okay, even though when we'll solve the band theory, then there will be some more modification in this term. This term comes out at En square tau f upon m. Okay, so still it is including all the electrons. Here he has included all the electrons. Okay, and when we use this using the Sommerfeld theory, calculate expression for electrical conductivity. Okay, again we are getting same expression, only the relaxation time here. Okay, he was calculating the relaxation time for all the electrons. Here only we are calculating relaxation time the electrons which are near to Fermi level. Okay, why we are doing so? Because we know that conductivity is sigma ne square by tau. Okay, and that is equal to sigma sigma is equal to ne mu, and what ne mu is what? Mu is your v by velocity, v by electric field, v by electric field. Okay, say vx. Okay, so that means if I want to write that my expression for velocity, so with the expression for velocity will be what in terms of this? So ne cancel. Okay, so I will left e tau ex upon m. Okay, so when you are applying electric field, okay, so the effect of electric field is to change the velocity of electron. Okay, when there is no electric field, then they are moving with thermal velocity. Now when you are applying electric field, okay, now those velocity distribution gets changed. Okay, so suppose earlier when you are applying, okay, this is your velocity distribution. Okay, when without external field, okay, without external field, so this is my velocity vx. I'm plotting in 2 dimension now. Okay, you can see sphere in 3 dimension. So without external field, this is, and if you do apply electric field, the velocity distribution changes little bit. Okay, not that much. Okay, so a little bit. Okay, so this velocity gets changed. Okay, well, delta vx, and the velocity of, and this velocity only changes only those electrons which are near to the Fermi level. Okay, and because our tau is related by lambda mean free path upon v. Okay, so only the particle electrons which are near to Fermi level, their velocity get changes more. Okay, changes more. So only Sommerfeld theory we are getting only this relaxation time. Okay, now the important point in electric conductivity is that dependence on temperature. Okay, even though we are using the formula here sigma equal to ne square tau f upon m, here we using the concentration whole the electrons. Okay, when we will do band theory, and there will see that not all the electron present in the solid contribute to the electric conductivity, only fraction of electron contribute to the electron conductivity. Okay, so this is your, so this is without external field, this is with external field. Okay, so I'm not discussing much of electrical conductivity. Okay, if it is required, I will discuss it again by when I use, I will, when I do the this band theory. Now I am going to discuss the temperature variation, temperature dependence of electric conductivity. That is most important, that is most asked in exams and interviews also. Okay, temperature dependence, okay, of electrical conductivity. Okay, now if you see the electric conductivity, okay, so electric conductivity basically depends upon many factors. Okay, one is lattice vibration. Okay, electric conductivity, okay, or resistivity, okay, affected by scattering. Okay, and the main source of the scattering in the metals are, or solids are, one is lattice vibration. Okay, and then second is lattice defects. Okay, lattice defects, and defects like vacancies, okay, intercital positions, dislocations, intercitals, okay, intercital, okay, and then you have dislocations.
Sir, what is the meaning of intercital position?
There have some gaps, na? Okay, either there is a vacancy, okay, or some foreign impurities are sitting in your lattice. Okay, intercital means the position which should be required by normal atom. Okay, that is, he is not there, somebody else is sitting on their position. Okay, either in a position or top of the lattice somewhere. Okay, so this lattice defect is vacancy, interstitial dislocations. Okay, and impurities. So these are the factors which affects your conductivity, because these are the factors responsible for scattering. Okay, but we are discussing temperature dependence, so these things do not change. Of course, with temperature, defect density changes. Okay, but we are assuming this is as it is. Okay, I'm neglecting this contribution. I'm only discussing the contribution of lattice vibration. Okay, so lattice vibration is main source of scattering with temperature, and this I'm talking at high temperature. This I'm going to discuss with high temperature. Okay, not in high enough, like still KBT is less than Fermi energy, but this temperature is a little bit high. Okay, so not frozen temperature, low temperature. Okay, those temperature I'm discussing. I'm discussing high temperatures. Okay, so high temperature, I told you there's lattice vibration. Okay, so this lattice vibration are the main. Okay, lattice vibration. Okay, or lattice vibration amplitude. Okay, vibration amplitude is the main cause of scattering. Okay, so as you increase the temperature, this lattice is vibrating. Okay, and once they are vibrating, okay, then they have cross section, scattering cross section. Okay, and as to increase the temperature, your scattering cross section increases. Okay, so and it reduces your conductivity. Okay, so now because I am considering high temperature, okay, so I can apply classical mechanics and I can write my amplitude, okay, as assuming simple harmonic oscillators. The amplitude I can write is half kBt. Okay, now I want my amplitude. Okay, because amplitude, because my scattering cross section is depends on the amplitude. Okay, so and at high temperature, okay, both I can write my omega is equal to Debye frequency. Okay, you said Debye frequency or Einstein frequency, they both are same, almost same at high temperatures. Okay, and their value we have seen, and their values when we were discussing this lattice vibration, we have seen this lattice vibration values are k theta d, okay, upon h cut, kb theta d h cut square. Okay, now just put this value here. Okay, half cancel, so let us say this capital M. Okay, so if I want d square, so d square will come out h cut square t, okay, m kb theta d square. Okay, and my scattering cross section, okay, my scattering cross section, scattering cross section means amplitude cross section. Okay, is proportional to d square. So I'm writing scattering cross section is s, so my s is proportional to d square. Okay, now what I can do, now let me write this mean pre-path. Okay, so let me first write scattering cross section. So scattering cross section is, say, constant, okay, multiplied by this one h square t m kb theta d square. Okay, So I'm doing simplest derivation so that we should know and understand. Okay. So this will give you now mean free path. You know, kinetic theory of gases. Mean free path depends on what? Number density as well as your scattering cross section. Pi d square. Scattering cross section. The exact expression is root 2 pi or root 2 and ns and root 2 root pi pi d square. What is the exact relation? Mean free path. You might have studied this in thermal physics. Okay, so I am only writing the proportional. Okay, so and tau is what? Tau is your lambda upon b. So now I want my tau. Okay, so I can write my tau is proportional to, okay, my tau is equals to lambda is ns, so I can write this is proportional to n v s. Okay, and if I write this will be equal to constant. Okay, so I will be having n v. If I write s, h square t m kb theta d square. Okay, so what we get? M kb theta nvf nbf. Okay, and here I'm taking this, so I can write this vf. Okay, vf. Okay, vf. This is the expression.
Sir, S comes in the denominator.
This is what s na. So I have to do opposite na. Okay, I have to reverse this one. Okay, so this will come m kb theta d square h square t. Now conductivity is what? Conductivity is sigma is ne square tau f upon m. You just can put the values here. Okay, so if you put the values, this n will cancel out. Okay, so you will have e square, you will have a vf, e square m, you will be having vf. Okay, mvf. Okay, then you will be having this is the mass, this is the mass of my electron. Okay, and this is mass of what is this mass? This is a lattice mass. Okay, so don't cut these things. Okay, e square mf. Okay, is atom mass, kb theta d square h square t. Okay, so this is my final expression for conductivity. Okay, and here I can see that my conductivity is proportional to 1 by t, or my resistivity is proportional to t. Okay, and of course this I have done for high, I have assumed classical things. So classic, because higher temperature classical Fermi statics both are same. Okay, so and for when you do high temperature, when my temperature is greater than theta d, okay, then or t is greater than theta d, then my resistivity is proportional to temperature. And experimentally also we see resistivity is proportional to temperature. While last time when we do classical theory, it was a root 2t. But still, what we are getting only high temperature. Okay, what about the low temperature? So how to write low temperature contribution? Okay, so if I want to write the low temperature contribution, okay, so the 1950, okay, Bloch has done some derivation. Okay, he has given some theory, and based on the theory he has derived the formula that is not that cannot be discussed in our course. Okay, so put the at low temperature, okay, you put the Bloch theory. Okay, Bloch's theory in order to explain the correct expression for electric conductivity. So the derivation I'm doing here. Okay, So for low temperature, this was earlier was high temperature. This is for low temperature. Low temperature. This will give both. Okay. So according to Bloch theory, the resistivity temperature is given by A T by theta D power 5. Okay. 0 theta D by T. Okay. X5 EX minus 1 and 1 minus E minus X dx. Okay. So he gave this formula of, and this formula, when we solve for temperature T greater than theta D, this will give me rho T is equal to T, and for T below theta D, this formula gives me rho T is proportional to T5. Here A is constant. If we solve this integration, we get these value. Okay. This dependence on temperature. Okay. So when I plot my electric resistivity versus temperature, okay. So at low temperature, it varies as a T5, and at high temperature is proportional to T. About debye temperature, it is proportional to T, and this is here rho. It will be small part. Okay. Small temperature rho is T power 5. Okay. This for metals. Resistivity rho versus T for conductor or metals. Okay. Now, a few things I need to discuss more before closing this chapter. Okay. So today I'm sending link for the test. Okay. Just see the test. Okay. So, Mithilesh, are you there? मिथिलेश ओके हाँ वो लिंक भेज दो मेरा थोड़ा मोबाइल डिस्चार्ज हो गया हाँ बच्चों को ऑनलाइन पे भेज दो प्रवेग ऑनलाइन पे
हाँ सर मैं भेज दूँ
ओके सो आई एम सेंडिंग लिंक प्लीज सी द क्वेश्चंस एंड सॉल्व देम ओके एनी क्वेश्चन टुडेस क्लास okay so I'm stopping here
Sir, this chapter was completed.
a little bit something I will discuss more okay or 10-15 minutes more and then we'll start band theory okay now some topic was remaining na? Some optical classical theory conductivity with frequency variation okay so some 10-15 minutes I need more okay
भेज दिए सर
okay thank you